Hello and welcome back to educator.com and welcome back to biochemistry. So we just finished discussing amino acids and peptides, and what I thought we would do is just do some more example problems with amino acids and peptides just to make sure we have a complete understanding, give us a little bit of a review of the things that we've done before, and just get familiar with it. So let's jump on in. Okay, so the first example, example 1. Okay, given the following data, answer the questions that follow. Answer the questions that follow. Okay, so we have 100 milliliters. Let me do this in blue, actually. So we have 100 milliliters of a 0.20 molar serine solution. At a pH of 1.60 is titrated with excuse me, a 2.0 molar sodium hydroxide solution. We don't care about the sodium, it's the hydroxide that we're concerned about. Okay, so the pK1 equals 2.21. We have a pK2, which is the pKa of the amino. That is equal to 9.15. And then I'll go ahead and give you the molar mass. I'm just going to write mm for molar mass. So m/m, and this happens to be 105 grams per mole for serine. Okay, now the first question that we want to ask is, what is the pI? What is the pI of serine? And draw the correct structure. Draw the correct structure. In other words, draw the correct structure at that particular pH, which is the pI. Okay, well, you've got two ionizable groups on serine. You have the carboxyl group and you have the amino group. So the pI, so that means, let me just draw the general. So you've got NCC, that, and you have that. Starting off at a pH of 1.6, these are both going to be protonated. Well, so this serine, sorry, I'll go ahead and just do an R there. We're not concerned with this serine yet. This is carrying a positive 1 charge. So a pI is the isoelectric point. It's the point where the net charge on the molecule is going to be 0. So the pI is going to be where the carboxyl group is fully, in this particular case, since you have two ionizable groups, it's where it's completely ionized. There's no H left on there at all, because then the carboxyl group is going to carry a -1. The NH3 plus is going to end up carrying a +1 for a net charge of 0. That's the isoelectric point. Well, with two ionizable groups, the isoelectric point takes place at the arithmetic mean of the two pKs. So you just add the 2.21, 9.15, and divide by 2. So we have the pI, oops, not a capital P, this is a small p. So the pI, the isoelectric point, is equal to pK1 plus, I'm always doing capitals, pK2 divided by 2. So 2.21 plus 9.15 divided by 2 gives us a pI of 5.68. There we go. So when the pH is 5.68, that means this serine molecule has a net charge of 0. The carboxyl is ionized, the amino is not ionized. Okay. Now let's go ahead and draw the structure of serine. So we've got the N, we have C, and we have C. We have our ionized carboxyl group. We have this one, which is not ionized. Let me make my carbonyl carbon a little bit better here. and then we go ahead and we have the H, and then of course we have CH2 and OH. This is our structure at 5.68. That's it. Okay. Let's see, part B. Excuse me. There we go. The pen didn't work there for a second. All right, so how many milliliters specifically of the sodium hydroxide solution, of the NaOH solution, have been added at this point? At this point, in other words, at the pI. Okay, so we started off with a pH of 1.6, and now we're at a pH of 5.68. That's the isoelectric point. We want to know how many milliliters of this 2 molar sodium hydroxide solution we've actually added to bring it to that point. Okay, so let's think about this. First of all, we want to know how many moles of serine there is in there, because it's going to depend on how many moles of ionizable groups that we have to titrate, because that's what a hydroxide is doing. The hydroxide is going in there and it's pulling off the hydrogen from the carboxyl group, and when that's done, that's going to be the isoelectric point, and then it's going to go and start pulling off the hydrogens from the amino group until it's done. That's the second plateau in the titration curve, which we'll draw in just a minute. So let's find out how many moles of serine we have. Well, we have 100 milliliters of a 0.2 molar solution. So we have let me do this one in red. So we have 0.100 liters times 0.20 moles per liter. So this will give us 0.02 moles of serine. Okay, well, serine has 2 ionizable groups, but 0.02 mole of serine contains 2 moles of ionizable groups. 2 moles of ionizable groups, right? You have the carboxyl and you have the amino. So with every amino acid, there's a minimum of 2 ionizable groups per mole of serine, which means that we have 0.04 mole of serine cancels more, 0.04 moles of ionizable groups. Well, the isoelectric point is when, in this particular case, you have 2 ionizable groups, is when one of them is completely ionized. So if you have 0.04 moles of ionizable groups, when half of them have been ionized, that's your isoelectric point. So that means, let me write that out. So one of these groups is fully ionized. That's what the pI means, isoelectric point. So you have 0.04 moles of total ionizable groups. Half of them have been ionized, which means 0.02. So 0.02 moles. Well, since we have 0.02 moles of ionizable group that have been ionized, that means, and it's a 1-to-1 ratio, 1 hydroxide per 1 ionizable group, right? It's pulling off 1 hydrogen. That means there are 0.02 moles of the hydroxide that I have to use. So let me actually specifically write that. So 0.02 moles of OH minus times, and it is 2 moles per liter. 2 moles of hydroxide per liter. What we end up with is 0.01 liters, or 10 milliliters of sodium hydroxide solution. There we go. That's our answer. I hope that made sense. At the pI, we know that one group is fully ionized. Well, I need to know how many moles there are. but each mole of serine actually brings 2 ionizable groups, so I have a total of 4 groups, 4 moles that can actually be ionized. Half of them have been ionized at the pi, at the 5.68. So of the 0.04, 0.02 moles have been ionized. Well, the 0.02 moles that have been ionized comes from, they've been ionized by 0.02 moles of hydroxide because it's a 1-to-1 ratio, OH plus H. That's what forms the water. This is a titration, acid-base titration. So that's where this comes from. I take the 0.02 moles of hydroxide, I multiply by the reciprocal of its molarity, and I get its volume. So 10 milliliters of NaOH are added. That tells me that in order to fully ionize the serine completely, I would just add another 10 milliliters. So I would need 20 milliliters of sodium hydroxide to completely ionize it. Okay. Let's see, part C. Hope you don't mind that I'm jumping around from color to color. Okay. Now, at what pH, actually, you know what? Let me go ahead and do this one in, let me go back to black. Part C. Excuse me. So at what pH is the average charge on serine minus 1/2? Okay, we want to know the pH where the average charge on the whole molecule is minus 1/2. Okay, we have 2 ionizable groups. So let me go ahead and just draw this out real quickly. So we have NCCO minus, I'm just going to put an R1 here, 3, actually let me go ahead and put the H, plus. Okay, so when both of these are protonated, it's carrying, the molecule is carrying a charge of +1. At the pK1, right, the pK1, that's when half of the carboxyl groups have been ionized, the other half is still protonated, so half protonated, half deprotonated. At that point, this side is carrying a charge of -1/2, right? Because if it were fully ionized, it would carry a charge of -1. But at the pK1, remember we said that's when half of the groups are ionized. The protonated and deprotonated form are in equal concentration. So instead of a -1 total, just solid -1, you get a -1/2. Well, -1/2 plus 1 gives you a +1/2. And then when this is fully protonated, that's the pi. Then you're going to have -1 and +1. That's going to be 0. Now, at the pK2, that means half of these are going to be ionized. So this side of the molecule is going to carry a charge of +1/2, and this side is already fully ionized because we've passed the pK1 mark. That is a -1 charge. So -1 plus 1/2, that gives us the -1/2. So the pH at which the total serine molecule is carrying a charge of -1/2 is the pK2, the 9.15. Now let me go ahead and write that out. So at a pH equals 1.60, that implies the charge on this molecule is +1 because nothing has been deprotonated. Okay, at the pK1, that implies the -1/2 plus 1 equals +1/2. That's the charge at the pK1. Well, at the pi, oh, I didn't even write it. Actually, you know what? It doesn't matter. I'll just go ahead and do that here. That's going to be -1/2 plus 1 equals a +1/2. And then at the pi, we have, of course, -1 plus 1. We have a charge of 0. And now the pK2. Okay, we have a -1 from the deprotonated carboxyl group. And then we have +1/2 from the half deprotonated amino group. And that gives us a +1/2. So at a pH, that's equal to the pK2, that's equal to 9.15. At that pH, the serine carries a +1/2 charge. That's it. I'm sorry, -1/2 charge. -1/2, that's the one we're looking for. Okay. Okay, part D. Draw the titration curve for this situation. Draw the titration curve for this situation. Okay, well, we know how to do this, not a problem. So we'll get and do this. We'll do something like that. Okay, let's mark off some. So let's do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'll just go ahead and put 11. And then, so let me see, this is 1. We said we started at about a 1.6. So 0.6, 2.12. So this 2.12, that's the PK1. And we said that the PI is 5.68. So I'll do 1, 2, 3, 4, 5, 5.68. So the PI is somewhere around there. This is the PI, 2.1. You know what? Let me write what these are here. This is PK1. This is 2.12, 5.68, and then 9.15, 6, 7, 8, 9, 9.15. So this puts our PK2 right there, and this is 9.15. So here we go. So we're going to start right about here. We're going to plateau out. Oops. We're going to plateau out, then we're going to go up, and then we're going to plateau again, and then we're going to go up. So it looks something like that. So we have, that's our PK1 mark. This is our PI, the isoelectric point. This is our second dissociation, the PK2, and that's it. It's at this point that we've added the 10 milliliters. The 10 milliliters of sodium hydroxide. We've fully ionized the carboxyl group. And then, of course, somewhere over here, we've added the 20 milliliters. So this is going to be milliliters of OH minus. And that's it. The titration curve, that's what it looks like. 2 ionizable groups, you have 2 plateaus. If you have 3 ionizable groups, you'll have 3 plateaus. That's it. Nice and simple. This point, and this point, those are the important points. PK1, the PK2, and the PI, the isoelectric point. You should be able to go back and forth. If you're given a titration curve with numbers on it, you should be able to say this happens here, this happens here, this happens here. Or if you're given numerical data, you should be able to produce the titration curve. Okay, let's see. E. The 10 milliliters of NaOH added to the solution at the PI, so the 10 milliliters to bring it to the PI, is how many equivalents? Okay, so in general chemistry, we mentioned this thing called an equivalent. We haven't really talked about it very much. In biochemistry, they tend to use it a little bit more. It's not really that big of a deal. You're not going to see it all that often. But equivalence just means how many. So 1 mole of serine, we said, has 2 ionizable groups, right? So it has 2 moles of ionizable groups. It has 2 equivalents of ionizable groups. So equivalent just means how much OH do I have to add for each H that is going to be deprotonated. In this particular case, I've ionized, in order to get to the PI, I've ionized 1 of the ionizable groups, so I've added 1 equivalent. If I ionize the whole thing, I've added 2 equivalents. That's it. It's just, instead of talking about specific volumes, like 10 milliliters, 5.6 milliliters, we just speak of equivalents. We're speaking more globally. A particular amino acid might have 3 ionizable groups. Therefore, in order to fully ionize that amino acid, I have to add 3 equivalents of hydroxide. 1 for the carboxyl, 1 for the alpha amino, and 1 for the, the R group. That's all that's going on. So in this particular case, 1 equivalent has been added to bring it to the PI. A second equivalent will be added to bring it to full ionization, not the PK2. Remember, the PK1 and PK2 represent half deprotonation. So these are the buffer regions. It's fully ionized here, and then the second one is fully ionized here. So that's the second equivalent. So this is really, really easy. This is just one equivalent. And they will often refer to it that way qualitatively instead of quantitatively. Quantitative, 10 milliliters. They're giving you a number. One equivalent is just, they're speaking about how many ionizable groups. That's all they're doing. Okay, F. Now, would a serine buffer solution, so let's say I went ahead and had a serine solution and I created a buffer solution out of it, would a serine buffer solution be appropriate for an experiment requiring, actually I'll write requiring for an experiment that needs to be maintained at a pH equal to 8.7. So if I'm running an experiment and I need to maintain the pH at about 8.7, would it be appropriate for me to use a serine buffer solution? In other words, I create a serine solution, I add enough acid or base to bring it up to this particular read. Is this a good buffer solution? Is serine a good buffer solution? Well, the answer is yes. And the reason is, well, take a look at the pKa. Where does this 8.7 fall? Well, I need it to be in the buffer region, so it either needs to be here, 2.2 plus or minus 1, so 1.12 to 3.12, that's the range of a good buffer, or in this case 8.7. So here the pK2 is 9.15, which means our particular buffer region, let me go ahead and this right here, it's going to be from 8.15 all the way to 10.15. So as long as the pH falls, if I need the pH to be in that range, the serine is actually a good buffer solution to use. So that's it. You're just looking at the pKa. That's all you're doing. Note the PI, this is not the buffer region. The buffer region is the horizontal region. The buffer region is actually the part that resists changes in pH the more you add. Notice 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. You keep adding hydroxide, the pH doesn't go up all that much. That's why. So in this particular case, experiment 8.7, yes, it falls within the range of the second pK for serine, so serine would be a perfectly good buffer solution to use in this particular experiment. Okay. So let's go on to example number 2. Example number 2. Okay. So quantitative analysis reveals that a certain protein contains 0.60% tyrosine by mass. I'm going to use the, oh, that's fine. I'll just go ahead and write by mass. By mass. Remember, M/M, sometimes as W/W. They often say a tyrosine by weight instead of by mass. It's the same thing. Okay, so further analysis estimates the molar mass to be about 135,800 grams per mole. And the molar mass of tyrosine is equal to 181 grams per mole. So this is the information that's given to you. Okay, so quantitative analysis reveals that a certain protein, it contains by mass 0.60% tyrosine. In other words, all of the tyrosine in there accounts for 0.6% of the total mass of the protein. Well, they do a little further analysis, and they're able to estimate the molar mass that's somewhere in the range of about 135,800, give or take. So the molar mass is 181 grams per mole of tyrosine. So the first question we want to ask you is, and this is the process that you'll use. Assuming the protein contains only one tyrosine residue, protein contains only one tire residue, calculate the minimum molar mass. The minimum molar mass of the protein. So what we're going to be doing, by assuming that we actually have just one tyrosine residue, we have the percentage. If we assume just one tyrosine residue, we can place a lower limit on the molar mass. And then from there, given this other bit of information, the 135,800, then we can go ahead and find out a little bit more about it. So let's go ahead and do the first part. Well, let's see. So a residue, let me do this one in red. So you remember a residue, when we speak about a residue, it's the amino acid minus the elements of water. So it is minus the elements of water, and the elements of water are H2O. So what you get is minus the elements of H2O. So what you end up with is 181 grams per mole minus the 18 grams per mole, which is water. So a residue of tyrosine actually is 163 grams per mole. Okay? Because when we form a peptide bond, when we're forming the protein, it's a condensation reaction. We're removing the elements of water, right? Reversive hydrolysis. So a tyrosine residue in a protein is actually missing an OH and an H from the original structure. So when we give the mass of the amino acid, it's 181 grams per mole. But when that amino acid is tied up in a peptide, in a protein, it's actually missing an oxygen and two hydrogens. So it's missing 18 grams per mole. So in this case, 163 grams per mole is the mass of the residue. Well, we take the 163 grams per mole divided by the total protein mass times 100, and they already told us that this is equal to 0.60 because it's 0.60% by mass tyrosine. Part over the whole, tyrosine over the whole, and when I solve for the mass, I end up with 27,166 grams per mole. So this is a minimum per mole. This is the min molar mass, and it's based on just using one tyrosine residue. Well, interestingly enough, I already have an estimation of the total molar mass, the 135,800. Well, if I know that I have a minimum mass of 27,166, now my second question to you is the following. How many tyrosine residues are there in this protein? How many tyrosine residues in this protein? Well, I have the minimum for one tyrosine residue. That's the relationship. I have the total, so I'll just take the total divided by the minimum, and that'll give me some, hopefully somewhere near a whole number. That's how many residues I have. Hope that makes sense. So let me do that on the next page, running out of room here. Actually, you know what? I should be able to do it here. That's fine. So I've got 135,800. That's the total mass, estimated mass of the protein. Based on this 0.6% for one residue, I've got 27,166 grams per mole, and when I divide that, I get about 4.99. So you're looking at 5 tyrosine residues. There you go. You use the basis of 1 to find a minimum, and then you work up, you divide it by the total. This is not altogether different than the empirical formula, molecular formula calculation that you do in general chemistry. Okay. Let's go ahead and do another example here. Let's go back to, actually let's go back to blue. I like blue a lot. Okay, so this is example number 3. Now, a peptide called methionine and kephalin was subjected to the following. Was subjected to the following procedures with the following results. With procedures with the following results. Okay. We're going to ask you to take these results, take a look at them, and deduce the structure of the methionine and kephalin. Deduce the structure of met and kephalin. Okay, so the first procedure that it was subjected to was 6 molar hydrochloric acid hydrolysis. So we basically just, hydrolysis. There we go. We basically just completely broke the we just released every single free amino acid. Let's see, so 6 molar hydrochloric acid hydrolysis, and we ended up with the following results. Methionine to glycine to phenylalanine to tyrosine, the molar ratios were 1 to 2 to 1 to 1, okay? So we weren't able to count how many of each, but we were able to get the ratios of the amounts of the amino acids in this particular analysis. So 1 to 2 to 1 to 1 meant to gly to phe to tyre. Okay. The other procedure we subjected it to was FDNB, and hydrolysis. I should write FDNB, then hydrolysis. Then hydrolysis, then we broke it up. Fluorodinitrobenzene, that's the Sanger reagent. And we ended up with the following. We ended up with DNB tyre. This molecule, this derivative of tyrosine, was detected, and also there were no free tyrosines. No free tyrosines detected. Okay, well, now our third procedure, we had fragmentation. We did fragmentation by pepsin. And pepsin breaks up the aromatics on the amino side. Okay. And what we ended up was with the following. We ended up with a dipeptide containing phe and met, and we ended up with some tripeptide. So we didn't sequence this. We didn't know the sequence. We just know that this dipeptide contains phe and met. We don't know which one actually comes first. And a tripeptide containing tyrosine and glycine in a ratio of 1 to 2. Okay, we need to deduce the structure. In other words, what's the amino acid sequence? Okay, well, let's see what we've got. So let me go ahead and go to the next page here. So let me see, our glycine is the one that's 2. So I'm going to write this a little bit. So I'm going to write the glycine first. So glycine to methionine to phenylalanine to tyrosine, that's going to be the 2 to 1 to 1 to 1. Okay, so I've got this. Well, they said that the FDNB gave me DNB tire. Okay, so this tells me that the tyrosine is the N-terminal residue. Tyrosine is the N-terminal. Is the N-terminal residue. Okay, so we know that it's tyrosine. Well, let me see. Here's something else they said. They said that there was no free tyrosine after we actually hydrolyzed it once we reacted it with the FDNB. Remember, the FDNB attaches to the N-terminal, and then once you break it up, everything comes apart. We detect this. We've labeled it, so we detect that. The others, we can also check to see what's in there, but there was no free tyrosine. Okay, and since there was no free tyrosine, that means there was only one tyrosine residue, and it happened to be the one on the end. So remember, we label it. The FDNB can only react with what's on the end. Once that reaction is done, that's when we break up the protein, and now you have a bunch of free acid. Well, if you can have a bunch of tyrosines that are also free in addition to the one on the left, but there's no FDNB in there, so it's not going to react with those. That's the whole idea. It reacts with the last one first, and then if you have any other free acids, then that tells you how many that you have. But in this case, there was only one DNB tire that was detected, but there were no free tyrosines, which means there's only one tyrosine. So this 2 to 1 to 1 to 1 is not just a ratio, it's exactly how much we have. We have 2 glycines, we have 1 methionine, 1 phenylalanine, and we have 1 tyrosine. So this is going to be a pentapeptide. In other words, we have 5 amino acids that make this up. Really, really nice. We know what the far left one is. It's going to be the tyrosine. Okay, now let's go ahead and take a look at our relationship. Pepsin cleaves, like we said, pepsin cleaves the phenylalanine, the tyrosine, and tryptophan, but we don't have to worry about tryptophan on the left. So when it cleaves it on the left, that means, in other words, if you have, okay, so if this is either phenylalanine or tyrosine, it's going to break it right there. So one of your fragments is going to have a phenylalanine or a tyrosine on the left. So one of the dipeptides, they said, contains phenylalanine and methionine. Well, we know that that dipeptide has to have a phenylalanine on the left. So we know that we're looking at phe and met. That's our dipeptide. Well, we also know that tyrosine, there's also a tyrosine and a glycine in a 1 to 2 ratio. Well, I've already accounted for the phenylalanine and the methionine. I know that tyrosine is on the left, so that I know that I'm looking at this, gly and gly. I know there's nothing to the left of the tyrosine because that is the N-terminal amino. Therefore, all of this information points to the following: tire, gly, phe, met. Tyrosine, glycine, glycine, phenylalanine, and methionine. This is the structure or the sequence of methionine and cephalin. There you go. I hope that made sense. You're just sort of putting pieces of the puzzle together. There's no one way to do this. You just have to use your intuition, use the things that you know, one piece at a time, put it together. This one was reasonably simple because we're dealing with a pentapeptide. Not going to be so simple like that. Other times, you're probably going to have to use a couple of cleaving procedures to get to see where you have overlaps. And in fact, that's what we're going to do next. Okay. So let's go ahead and take a look at another example of a sequencing of a peptide, but this one a little bit more complicated, a little bit longer. So let's see what we've got. Okay, this one I wrote out because there is a lot more analysis going on. So let's take a look. So glucagon is a peptide hormone that is secreted by the pancreas in response to low levels of glucose in the blood. It induces the liver to convert glycogen to glucose. Glycogen is a carbohydrate, glucose is a carbohydrate, glycogen is made of glucose, and release it into the bloodstream. Glucagon was subjected to several analytical procedures with the following results. Use these results to deduce the amino acid sequence of glucagon. So glucagon just does the opposite of what insulin does. If the blood sugar gets too high, insulin is released. If the blood sugar gets too low, glucagon is released. It's a way of maintaining the blood sugar level at some stable level, hopefully. Okay, so in this particular case, we did a 6 molar hydrochloric acid hydrolysis of the whole thing and an amino acid separation. So we were actually able to count the number of amino acids. So here are the results of the hydrolysis and the counting. Histidine, serine, GLN, GLY3, ASN, Phe, asp, these are all the numbers that we have. Okay, so now let's see what other analyses. So we did an FDNB, and we ended up with a DNB his. Okay, that's good. So we have that. So we know that histidine, and we notice that we have the 1 histidine. So in this particular case, that 1 histidine happens to be the N-terminal, so that's some good information. We did a couple of fragmentations on this using 2 different enzymes. We used the ASP-N protease, and what it does is that fragments, that cleaves the ASP, that cleaves the protein to the left of the ASP. N, that's what the N means, the amino side. So when we fragment it, there's going to be, the fragment is going to start with an ASP. Okay. So let's see here. Fragmentation and Edmonds sequencing gave the following fragments. Okay, so in this particular case, we not only fragmented, but we also sequenced it, and we came up with these fragments. So here we're just using the single letter designations for the proteins. And don't worry about them if you still haven't memorized them. I mean, at some point you're going to have to, but no big deal for right now. So this is the first fragment, that's the second fragment, the third and the fourth. So this A1, A refers to the ASP-N protease. And then we go ahead and take an intact protein and we subjected it to a second fragmentation procedure with trypsin. Now trypsin tends to break lysine and arginine. It cuts them at the lysine and arginine residues, and it cuts the carboxyl size, so to the right of it. So in any particular fragment, you're going to end up having an arginine or a lysine at the end. Okay, so let's see what we've got here. And those fragments gave us this, and this, and this, and this. Excuse me. Well, okay, so let's see if we can put this together, and let's see if we can find some overlap between these fragments and these fragments. So let's see what we've got. Let's see what we can do. All right. Well, we know that this is what we know. So we know that the DNB histidine means that histidine is the N-terminal residue. Yes, so that's nice. Means that his is the N-terminus of this particular protein, which is really, really great. And we have a couple of the fragments, so let's see, A1, and if I take a look at T3, I notice that T3 is the one that actually has the H on the left, so we know that that fragment goes first. That's fantastic. So we've already taken care of about 1/4 of this. So let me go ahead and list this as, so I've got H, S, E, G, T, F, T, S, D, Y, S. So this is the T3 fragment, okay? So the T3 fragment goes there. Now let me go to blue. Okay, I take a look at some of the fragments on the A side, and I notice that this this thing, this T3, overlaps A4. So I'm going to go ahead and put the overlap A4 right underneath. So it's going to be DYS and then KYL. Okay, now let me switch colors again. So I check, now I go back to my T and see if there's an overlap there. Turns out there is. So this actually overlaps the T4 fragment. And again, you can switch back and forth and see that this is absolutely correct. So in this particular case, I write the overlap this way. I just tend to do it in a stair-step fashion and then just read it off at the end. You can do it any way you like, however you want to put the pieces of the puzzle together. DSR, okay. Now let me see. I take a look at my A fragments, and yes, there is an overlap here. So let me go back to red. So this overlaps A3. So I go ahead and write A3 underneath. That's going to be DSRRAE. And let me go back to blue. Okay, this one overlaps T1. Overlaps T1. So I go ahead and write T1 underneath. I've got A, E, D, F, V, E, W, L, M, N, and T. And this one, it overlaps A2. And that'll be my final sequence here. A2. And of course, that's the, let me do this in black. So this is going to be the D, F, V, E, W, L, M, N, and T. And there you go. Now I just sort of read it off and just make sure to skip the overlap part. So there, and there, and there, and here. Now I just read it off. So I'm going to do this final one in, I guess I'll do it in red. How's that? So our final sequence is H, S, E, G, TFTS, T, F, TS, D, Y, S. I have that overlap, so it's going to be KYL, KYL. I have the YL, so it's going to be DSR, DSR, R, A, E, and then the rest, D, F, V, E, W, L, M, N, and T. There you go. This is the final amino acid sequence of glucagon. Again, hydrolysis to count, Sanger reagent to find out what the N-terminal is. Let me go ahead and make sure that this is a little mark here. Fragmentation with one enzyme or a chemical procedure, fragmentation with another enzyme, check for some overlaps. You're just sort of putting it together. Again, I like to put it together in a stair-step fashion like this, and then just read it off. There you go. Pretty straightforward. This is just, there's nothing difficult going on here. It's just a question of putting the pieces together. That's it. Okay. So let's see what we've got here. Okay. Let's close this off with one final example. Excuse me. Let's go ahead and do this in blue. And hopefully we can fit this on one page. So example 5. I want to create as much room as possible, so I'm going to say, oh, that's fine. Okay, give a schematic for the Merrifield synthesis. For the Merrifield synthesis of the following tripeptide: glyphenol. So glycine, phenylalanine, leucine, and use only the three-letter designations. You don't actually have to write out the structure. Not a problem. Okay, so let's go ahead and do it. So remember, the Merrifield synthesis, we actually synthesize from right to left, from the carboxyl end toward the amino end. So we're actually going to be starting with, oops, let's do this in red. We're actually going to be starting with leucine, then phenylalanine, then glycine. It's the opposite of how nature does it. Nature goes amino to carboxyl. Merrifield goes carboxyl to amino because we're attaching the first one to an insoluble bead. Okay, so let's start off over here. Hopefully I can do it. So let's start off with our leucine. Leucine. And I'm going to react it with our FMOC chloride. And that's going to give me FMOC leucine. And then I'm going to react this with a bead. Okay, those polymer beads. So what I end up with is FMOC, leucine, and then the bead. And then I'm going to subject this to trifluoroacetic acid or mild base to deprotect that leucine, get rid of the FMOC. So I end up with leucine and the bead. Okay, now over here I'm going to go ahead and do this in black. Over here I produce, now I'm going to go and I'm going to work with my phenylalanine. So I'm going to take phenylalanine and I'm going to react it with FMOC chloride. So I'm going to protect its amino group. So I get FMOC phenylalanine. Then I'm going to react it with the DCC, dicyclohexylcarbodiamide, and I get FMOC, I get the phenylalanine, and I get my DCC. And this is what I'm actually going to take and react. Goes in here, DCC comes out, and what I'm left with is FMOC, I'm left with Phe, I'm left with Lu, and now it's still attached to the bead. Okay, I subject this to trifluoroacetic acid to release this FMOC. So I end up with phenylalanine, leucine, and I end up with a bead. Now I'll go ahead and prepare my second amino acid. That's going to be glycine. So I'm going to react glycine with FMOC chloride. So I'm going to get FMOC gly. Notice that the FMOC is on the N side. Okay? And then I'm going to react this with the DCC to activate the carboxyl, so it'll actually react. So I end up with FMOC, gly, DCC. I take this and I react it with that, and DCC comes out, and what I'm left with here is FMOC, gly, Phe, Lu, and a bead. Okay, you know what? I can keep this on one page. It's not a problem. Well, that's fine. Let me go ahead and do the next page. So we've got FMOC, we've got gly, we've got Phe, we've got Lu, and we've got a bead. And we want to go ahead and subject that to trifluoroacetic acid. And we end up with glycine, phenylalanine, leucine, still attached to a bead. And then we wash this with some hydrofluoric acid. We end up releasing that. We end up breaking this bond, the leucine and bead bond, and we end up with our final glycine, phenylalanine, and leucine. There you go. That is a Merrifield synthesis of that particular tripeptide. Okay, well, that takes care of the examples for the amino acids and peptides. Thank you so much for joining us here at educator.com and biochemistry. We'll see you next time. Bye-bye.